Good morning, everyone. And as the Patricia said, I am Flavio Rusch, and I came from São Paulo. I work on the NeuroMath, which is the research center of neuromathematics linked to University of São Paulo. In the next minute, I will talk about some of my preliminary results in my research theme, whose the title is Self-Organized Criticality in Hierarchical Modular Networks of Galves-Löcherbach Neurons. And for such that, I divided my speech, my talk, into 4 parts. I will start with a brief overview and motivation, talking about some considering, and then I will present the network architecture and talk about the network itself, and the implementation of algorithm, then the network dynamic, presenting the stochastic neurons, and at last, the results about the static model. So, some considering. Experimental study generally agree that the cortical networks have a hierarchical modular architecture. On the other hand, experimental study were able to measure neuronal avalanches, which is responsible for self-organized the system into a critical point. The neuronal avalanches obeying a Paulo law distribution is a signature of self-organized criticality. And then after this considering, the following question arises. Can we construct hierarchical modular cortical network models that self-organize to a critical point with neuronal avalanches with Paulo law distributions? That's our main question that we are interested to answer. So, about our network architecture. We started with a random network of n equals 2 elevated to 10 neurons. The neurons were connected with connectivity epsilon equals 0.01. And here epsilon gives the synaptic probability of any pairs of neurons in the network. This type of network is called a network of hierarchical level, or each equals 0. And the ratio in the network, the ratio of excitatory to inhibitory neurons is 4:1, which is based on the evidence that approximately 20% of cortical neurons are inhibitory. So the implementation algorithm of the network. Networks of higher hierarchical levels are generated by the following algorithm. First, we randomly divide each module of the network into 2 modules of equal size. And then with probability Ri or Ei, we replace each intermodular connection, Ij, by a new connection between I and K, where K is a randomly chosen neuron from the same modules as I. And recursively, we apply the step 1 and 2 to build networks of higher hierarchical levels, H equals 2, 3, and so on. And the network with a hierarchical level H has, hence, 2 elevated to H modules. And here in the top row, we might see a schematic representation of the several hierarchical modular networks. For H equals 0, the network is the Henri type, and as long as the hierarchical levels of the network increase, the number of modules of neurons increases as well. These modules have a hierarchy of connections. Modules that are topologically closer are denser than between more topological distant ones. For instance, H equals 3, these 2 modules represent 2 closer modules than those 2 modules. And here in the bottom row, we have the respective adjacency matrix. This type of matrix shows which kind of synapses each neuron in the network realize to the other neurons in the network. And hence, here, the blue dots represent the excitatory connections, and whereas the red dot represents the inhibitory ones. Oh, yes. And the information that the figure highlights is that the inhibitory connections can occur only inside of each module, while the excitatory connections can occur inside and between the module. And so here we can see the inhibitory and excitatory connections, and this here we can see the excitatory connections between these two modules, and so on. So we used in our work RE equals 0.9 and Ri equals 1. So as I said, so the intermodular connections are exclusively excitatory. As we can see, as H increases, the number of modules increases as well, and modules are encapsulated in groups of modules. Inhibitory connections occur, as I said, strictly within modules, and so they are local, while excitatory connections can be both local and long range. About the network dynamics, the stochastic neurons. The Galves-Löcherbach neurons introduces stochasticity in their fire neurons in a different way. Instead of noise inputs, they assume that the firing of the neurons is a random event, whose the probability of occurrence is a firing function, depends on the membrane potential, V. And so, by subsumming all sources of randomness into a single function, the GL neuron model simplifies analysis and simulations of noise spiking neuronal network. So, let xi be a firing indicator. If xi of t equals 1, neuron I spikes at the time t. Otherwise, does not spike. In that work, the firing function adopted depends on the membrane potential of the I neuron, Vi of t, and the neuronal gain of the neuron I at the time t, gamma I of t. For the mathematical convenience, we use the rational function given by the equation 1. And the membrane potential evolves according to the equation 2. And you can think, if the neuron J fires, then xj of t equals 1. This event increments by a wij the potential of every postsynaptic neuron that has not fired at the time t. The potential of the non-firing neuron may also integrate an external stimuli, I, and a part of these increments, the potential of the non-firing neuron decays towards 0 at each time step by a factor mu. Is an element of 0 and 1 towards to 0. Yeah? So mu here models the effect of current leakage. So this model of the neurons is a LIF, leakage integrating fire, stochastic. So as I said, mu is an element of 0 and 1, is the leakage parameter, and I the external input. The synaptic weights are wij, positive for excitatory and negative for inhibitory synapses, and their magnitudes is W. We adopted in this work two homeostatic mechanisms in order to turning the critical point into an attractive fixed point of some homeostatic synapses, homeostatic dynamics, sorry. So the two mechanism is the dynamic synapses, given by the equation 3, and the neuronal gain, given by the equation 4. Note the neuronal gain enter in the equation 1 in the firing function. So the variable tau is the recovering time. A is the asymptotic value, the same for inhibitory and excitatory synapses. And U, larger than 0 and less than 1, is the fraction of synaptic weight lost when the presynaptic neuron J fires. When xj equals 1. The static model. We call static model the model in which mu is equal to 0 and there is no external stimuli. I equals 0. In such case, the firing rate, the activity of the neuron I, is given by the sum over all presynaptic neuron J, neighbor of the neuron I. Here, K is the number of neighboring neurons of the neuron I. And the activity of the network is given by the sum of the activities of all neurons in the network. It's the sum of all firing rates. Now the results. A previous mean field analysis of the model without inhibition has shown that the product gamma times W equals 1 is a critical line of a continuous absorbing state transition. And here we can see, independently of the hierarchical levels of the network, independently of modularity, the absorbing state gamma 0 equals 0 loses stability after the product is larger than the parameters, the critical parameters gamma critical, W critical equals 1. This is the first characteristic, suggestive criticality. On the other hand, the activity of the networks increase as long as we increase the modularity of the network. This occurs because since the connections are rearranged inside of each module, the neurons are rearranged inside of each module, the connections increase in each module, and so hence the activity increase. And here we calculate the avalanche size distributions for different levels, and we know that as long as the hierarchical levels of the network increase, we kind of lost the power law distributions behavior. So here for h equals 0, we have a value of the exponent of the power law distribution approximately 1.5 for h equals 0, which is suggestive of criticality. And when I say about the power law distributions and avalanche, in neuronal avalanche, I would like to present you a didactic example. So we have here 3 types or 3 sizes of the neuronal avalanches for the h equals 0. 3 types of avalanches with different size and duration. We can see the activity propagates in the cascade of events. Here's the one. Small. And bigger one. And so the exponent that represents this behavior is approximately 1.5 at last. The bigger. Right? And so, as long as the modularity increases, the behavior of the system becomes subcritical, as we can see through the tails of the distributions. Begins to be a subcritical. And here the duration, the avalanche duration distributions, and we can see almost the same thing for the h equals 0, tau d equals approximately minus 2 is suggestive of criticality. And when the modularity increases, the system becomes more and more subcritical, losing the power law distribution behavior. So here is exponential behavior. And at last, I would like to show to you the fine-tuning of model. Here we have a dynamical case, the temporal evolution of the neuronal gain. The dashed line represents the critical value for the gamma. And so we can see from this figure is that the system, the dynamic system, is not a critical or subcritical, but is a supercritical. So here we present a self-organized supercriticality because the gamma here is towards to gamma larger than 1. And I think that is it. I would like to formally thank to FAPESP, especially for the Neuromat, and for FAPESP for the grant, and my reference, and thank you for your attention.
Thank you, Flavio. Any questions or comments?
I have a question. The first bifurcation you showed, you had half a pitchwork. Could you please, yes, this one. Could you please explain again the role it plays in your analysis?
Yes. Sorry. Activity here is the order parameter of the system. The order parameter of the system. Which this figure highlight is when is occurrence the phase transition between two states. Between the absorbing state, there is no activity, activity is equal 0, and when we have the activity phase. As I said, works showing mean field analysis for every type of models without inhibition, without inhibitory connections, has shown that for gamma times W equals 1 is a critical line. So for W larger than 1, we expected we see a phase transition. And so here represent some type of criticality of the system. We don't know if the system is supercritical or subcritical or critical, but is an evidence of criticality.
Other questions?
Thank you for your talk. I found very interesting to study the modular architecture because for neurobiologists, something that I've been always surprised is concerning the pathophysiology. I want to say, so for example, in some pathology like Alzheimer's disease, where we have degeneration, is specific to cortex or to the entrance of the hippocampus, which means the entorhinal area. And we really think that the architecture is behind this fragility of the brain. For some also other pathology like epilepsy, so the way that the neurons are arranged we will have
some kind of degenerescence.
will have an influence on the propagation of the epilepsy.
Yeah.
So I really think that is very interesting to study this, and it could have many consequences on the physiopathology. So thank you.
You're welcome. If allowed to say, I show to you just the static model. You have to see that I don't present the dynamic results. And I think interesting thing is that when we applied these two mechanisms in the architecture for different external stimuli, we can see a synchronization pattern inside of each module. For instance, for H equals 3, we have 8 modules of the neuron. And so each module synchronizes your activity in a different way. Is a quite interesting results there, where so far I don't understand what's going on in the network for this. So it's pretty interesting. Thank you for your argument.
Yeah, I have a related question about how you generate the connectivity, in the sense that it appears to be very homogeneous pattern. And so did you think to have more not inhomogeneous, heterogeneous patterns? And is it related to something you think about?
It's a good question. Thank you for that. The network, there is no homogeneity. Is a random sparsely is a network, is a sparsely random connected network.
Can you go back and show how you generate this connectivity?
Here or here? Here, I think. Is a random network, sparsely connected. And so I think that is not homogeneity.
Do you have a probability of connection?
Because we divide each module randomly.
Yeah. Is the same?
All right.
It is the same probability
then yes,
that you have.
yes. I think that you mentioned the.
I mean, even if it is sparse, I don't say it's complete graph, but it's you have a probability of choosing or not the connections. It's kind of Erdős-Renyi, I'm not sure.
Yeah. Yes, we have a probability, a connectivity 0.01, and
yeah. So yeah, homogeneous in this sense that there is the same probability of choosing. And
yes, yes.
It's okay. Thank you.
Thank you a lot. We need to go to the next speaker, but thanks again.